In this lecture, I'm going to be starting Chapter 11 in this course on math methods. So Chapter 11 in our textbook is a topic of special functions. So what you find is that in your course of studying physics, or even doing physics, doing like physics research for a living, that a lot of times in your calculations you come upon certain functions that come up and that you see all the time. And one of the functions is the factorial. You see that all the time. An example of this is when you take thermodynamics. What you'll find is that you'll say, what is the natural log of the factorial function? And what we find, we'll say later on in this chapter, is that I could approximate this as n times the natural log of n minus n, which is a much easier solution to use than trying to figure out how to take the factorial and then take the natural log of it. Instead, let's just use natural logs on numbers instead of factorials. So that's what we're going to be dealing with. So special functions just means commonly used functions, or functions that come up all the time. So the first one we're going to study is the factorial. So the factorial, by definition, is to multiply all of the numbers less than that number. And this is only true for integers, so positive integers. So n is going to be greater than or equal to 0. So we can come up with some examples. If n is equal to 3, then 3 factorial is 1 times 2 times 3, or 6. 5 factorial, 1 times 2 times 3 times 4 times 5. Now if I notice that 3 factorial was already in here, then what I really have is 6 times 4 times 5, or 24 times 5, or 120. So just a few of the examples, and you've probably seen these before. This probably came up in high school when you're taking like pre-calc. Really what it comes up to is when you start something like the binomial equation, then you would often take combinatorial, and what you find is that the combinatorial equations deal with the factorials all the time. Okay. Now it turns out there's actually another way that we can study the factorials. So for example, let's say we have a number, alpha, which is greater than 0, and I now want to integrate from 0 to infinity of e to the minus alpha x dx. So that one is pretty straightforward. We would just get minus 1 over alpha, e to the minus alpha x back again. And then if I apply the limits from 0 to infinity, then what I would get is minus 1 over alpha, e to the minus infinity, minus e to the 0. So I can rewrite this as minus 1 over alpha, and then 1 over e to the infinity, minus 1. 1 over e to the infinity is really just 1 over the infinity. So I would have minus 1 over alpha 1 over infinity minus 1, or minus 1 over alpha, 0 minus 1, and minus 1 over alpha is just times minus 1 would just be 1 over alpha. Okay, pretty straightforward. Okay, so let's try take the derivative of both sides of the equation now with respect to alpha. So we're going to take the derivative with respect to alpha of the integral 0 to infinity e to the minus alpha x dx, and then the derivative with respect to alpha of 1 over alpha. So when I do that, I can pull this derivative inside the integral because the limits don't depend on alpha, and I get 0 to infinity d alpha e minus alpha x dx. On the right hand side, I just get minus 1 over alpha. So what I get is when I take the derivative, I get the integral minus x e to the minus alpha x, and then that's equal to minus 1 over alpha. I can cancel the minus sign on both sides, and I get the integral of x e to the minus alpha x dx, which is now equal to 1 over alpha squared. If I differentiate again, so if I take the derivative one more time with respect to alpha, I would get minus x squared. Whoops, sorry. Don't want to skip steps. And we get this. So now I get the integral of minus x squared e to the minus alpha x dx, which is now equal to minus 2 over alpha cubed. Again, if I eliminate the minus sign on the other side, then I would get x squared e to the minus alpha x dx, and that's 2 over alpha cubed. We could differentiate again. If we differentiate again, then what you would get is this pattern where I would get x cubed e to the minus alpha x dx is equal to now 2 times 3 over alpha to the 4th power, and which I can rewrite now as 1 times 2 times 3 over alpha to the 4th, or 3 factorial over alpha to the 4th. So what we end up with is a general equation, and our general equation is x to the power n e to the minus alpha x dx is equal to n factorial over alpha n minus 1. I'm sorry, n plus 1. N plus 1. So now you can apply that to anything. So in that, really, what we have is, one, we've solved a very general form of this integral where I could pick any n I want. So, if n is 5, so the integral of x to the 5th, e minus alpha x dx, is equal to 5 factorial over alpha to the 6th. And I already said the 5 factorial is 1 over 20 is 120. Now alpha to the 6th. So that's pretty good. I mean, this trick of differentiating the integral actually gave us, a general formula to solve an integral of x times an exponential. But more importantly, or for this discussion about factorials, let's say let alpha equal to 1. Okay, so if we let alpha equal to 1, then we get the integral of 0 to infinity of x to the n e to the minus x dx. Okay. And on the other side, I get n factorial 1 to the power n plus 1. But 1 to the power of anything is just 1 again, and so that's equal to n factorial. So that's really interesting, because now what we have is a formula for the factorial, which is now an integral. So the factorial is no longer just, let's just define it as the product of a bunch of positive integers, but now it's actually the integral of this continuous function, an integral from the limits of 0 to infinity. And so now we can try and apply this to into numbers that don't quite fit into the positive integers greater than 0. So the first one we can try is 0. So what if we set now n equal to 0? So that's pretty interesting. So if we set that equal to 0, then what we get is 0 factorial is equal to the integral from 0 to infinity, x to the 0, e to the minus x dx. And when we do that, x to the 0 is just 1. So that's the integral of 0 to infinity of e to the minus x dx. So if I take that integral, I now get minus e to the minus x evaluated at the limits of 0 to infinity. So let's put those limits in. So I get e to the minus infinity minus e to the 0. We already said that e to the minus infinity is 0. So that disappears. So we're left with minus e to the 0, or positive e to the 0, or 1. So we get this result, which you've probably told when you were much younger, that if you take the factorial of 0, then the answer should be 1. And now you know why. And because this is one of those cases where it doesn't fit the definition. The definition was 1 times 2 times 3 times all the way up to n, but 0 doesn't fit into that because there are no numbers less than 0. Then you get the negative numbers, negative integers, and that doesn't seem to fit my prescription of what an n factorial is. But now if I use the new definition of n factorial as the integral 0 to infinity of x to the n e to the minus x dx, now I can solve for the value of n equals 0. So what we're going to do next is to expand this even further and say, what if I want to consider a negative number? How do we take the factorial of a negative number? Or how do we take the factorial of a fraction, which is not really a real number, but is still a fraction which doesn't fit into this. If I had how do I count a fraction from, so if we had 3/4 factorial, is that, that's less than 1, it's bigger than 0. What are we going to do? So that's what we'll find out in the next lecture.